Thank you very much for that nice introduction and also the opportunity to speak here today. I'm going to be talking about the Kakeya set conjecture, primarily in part 3. So it's a question that many people have thought about, and I'll discuss some of the historical progress on this question, and also some recent work by Hong Wang and myself resolving the Kakeya set conjecture in part 3. So the starting point is something that perhaps everyone in this room is now familiar with, and it concerns objects called Bezukovich sets or Kakeya sets. These are synonyms. And these are compact sets in Rn that contain a unit line segment pointing in every direction. So these don't have to be mysterious. For example, a closed disk of radius 1/2 or larger is an example of a Bezukovich set. But rather surprisingly, back in 1919, Bezukovich constructed an example of a Bezukovich set in the plane that has the vague signature 0. His motivation for doing this concerned a question in Riemann integration that's not so interesting for us to discuss and adjacent areas. So what Bezukovich did is he showed there exists, he didn't call it a Bezukovich set, but there exists a Bezukovich set in the plane with Lebesgue measure 0, and what that means if you take its delta thickening, so in everything I say delta is going to be a small parameter, I'm going to be interested in the asymptotics as delta goes to 0. So if you take the delta thickening of a measure 0 compact set, then that measure goes to 0 with delta, and we're going to be quite interested in the asymptotics as a function of delta and how this goes to 0. So an immediate consequence of Bezukovich's construction, I'm just writing down first year calculus quantifiers. What does it mean that the volume of this delta thickening goes to 0? It means that if you give me any positive number eta, I can find delta sufficiently small so that the delta neighborhood of the set has volume at most eta. And so my original Bezukovich set, we're still in the plane, it contains a unit line segment pointing in every direction. If you take its delta thickening, that's still true, but more is true. It contains the delta neighborhood of a unit line segment pointing in every direction. And from this, I can extract a set of unit line segments pointing in delta separated directions, each of whose delta neighborhoods is contained in my delta thickening of the Bezukovich set, and I can take a maximal collection. So there's roughly 1/delta of them in the plane. I don't care about constants. Each one of these has area delta, so what this means is the sum of all of these rectangles, so dimensions 1 times delta, the sum has area roughly 1, but the volume of the union is quite small because it's contained in this delta thickening of a Bezukovich set, and we know that the volume of that goes to 0 with delta. So I'm going to call this the Bezukovich compression phenomenon. We can find these rectangles, or more generally tubes, the delta neighborhoods of line segments pointing in different directions, the sum of whose volume is roughly 1, but the volume of whose union goes to 0 as a function of delta. And the Kakeya set conjecture can be thought of as a way of quantifying just how much Bezukovich compression can occur. So the way that conjecture is typically stated is every Bezukovich set or every Kakeya set in Rn has Minkowski and Hausdorff dimension n. And that's very terse, but in practice, the way that most people in the field think about it is this discretized version. So in Christov's Ladaccio, he called it the discrete version, but I'll call it the discretized version. And it involves some quantifiers. But the idea is I'm interested in delta tubes. So these are the delta neighborhoods of unit line segments in Rn. I've drawn an example on the right here. And they're pointed in delta separated directions. And I'd like to understand the relationship between the volume of their union and the sum of their volumes. And so an enemy gets to arrange these tubes in space however they see fit. And they're trying to make the volume of the union as small as possible. How good of a job can this enemy do? And if the enemy is not so competent, then maybe the tubes are entirely disjoint and you have equality on the left and the right. If the enemy is rather smart, they can overlap a bit, and maybe the left and the right differ by some positive constant, but if the enemy is Bezukovich, he's very smart, and he was able to arrange these tubes so that the volume of the union, that this ratio goes to 0, but the conjecture is no matter how clever you are at arranging these tubes, it goes to 0 as a function of delta, but slower than delta to any fixed power. And so that's what's being described in these quantifiers. And this double squiggle notation here is just a short form for that. So an example to have in mind is, as delta goes to 0, 1/delta goes to infinity rather quickly. Log of 1/delta goes to infinity but rather slowly, and the reciprocal of that goes to 0 but rather slowly. And so this double squiggle you should think of as hiding something like the reciprocal of log of 1/delta, or maybe some power of that. And so what this is saying is Bezukovich compression can occur. This is what Bezukovich discovered, but the maximum possible amount of compression is at most logarithmic, or something close to logarithmic. So that's what the Kakeya set conjecture says, at least the way that it tends to be thought about today. So you could ask, why is this a question you might care about? And what I said is, well, you might not care about Bezikovic sets, but they do care about you, at least if you're a harmonic analyst. And so when I was first learning, I guess first year analysis, I learned about the Cantor set, and this seemed like a very surprising object, that there were many intuitive statements that were false, and the counterexample was a Cantor set, and that kind of revealed a certain richness in questions that otherwise seemed straightforward. And I would argue that the existence of measure zero Bezikovic sets play a similar role for questions in harmonic analysis, where there's many natural statements, many of them were proved in one dimension, and you might imagine, well, what's new about two and higher dimensions? Surely the natural analogs of those statements remain true. And in some instances, that is not the case, and the counterexample comes from measure zero Bezikovic sets. So one example was Charles Pfefferman's rather surprising construction showing that the Ball multiplier is unbounded once you're in two and higher dimensions in LP for all p not equal to 2. Christoph mentioned that as well. And I won't tell you exactly what Pfefferman did, but his construction makes essential use of measure zero Bezikovic sets. And then for those that were here just a few minutes ago in Rougen's talk, he talked about how waves interact and the important work of Jean Bourgain and many others of it, perhaps most notably Bourgain started in 1991 with a wave packet decomposition for understanding Stein's Fourier restriction conjecture and closely related questions about solutions to the Schrödinger equation and the wave equation. And again, you can take a function which satisfies the free Schrödinger equation or equivalently has Fourier support on a paraboloid. A useful way to analyze it is to decompose it to a sum of simple pieces called wave packets. Each one of these wave packets is fairly straightforward to analyze on its own, but the way they can interact with each other can be extremely complicated. And in particular, you could arrange them to interact with each other like a collection of tubes pointing in different directions. So the Kakeya set conjecture is hiding inside of these questions involving how waves interact. And so if you care about those questions, you're forced to grapple with the Kakeya set conjecture. There's also questions in analytic number theory I won't get into, in which Kakeya sets are lurking in the background. And so what we'd like to say is, okay, you have all these natural conjectures, and it turned out many of them were not true because of the existence of these measure zero Bezikovic sets. But perhaps smoothing things out a little bit will salvage these conjectures, and that seems possible. But if the Kakeya set conjecture is false, so if these tubes can compress even more than is suggested by the Kakeya set conjecture, then all these other conjectures become false again. So there's many interesting conjectures which imply Kakeya, or the falsification of Kakeya would rule out all these conjectures. So that's all I'll say about the motivation for the Kakeya set conjecture. I'll spend the rest of my time talking about the conjecture itself and some pieces involved in its proof in R3. And sometimes to solve a problem, you want to find the correct generalization, which allows you to think of it in a new way. And so the discretized Kakeya set conjecture, it's a special case of a slightly more general question. It's intentionally vague here. So let's say I have a set of congruent, perhaps convex subsets of Rn, or just general subsets, or subsets from some nice class. But let's say I have a collection of congruent convex sets in Rn. What hypotheses are needed to ensure that their union is almost disjoint? And I have this double squiggle here, which perhaps is a bit vague, but you can imagine this is related to the eccentricity of these convex sets, for example. And the Kakeya set conjecture is an example where your convex sets are all congruent copies of a tube, but there's many other questions you could ask. And one possible condition that you could impose is something that Hong and I call the Katz-Tau convex Wolf axiom. So I'm defining that for you now. So if I have a collection of sets in Rn, you could think of them as being convex, but the definition makes sense in either case. We say that this set satisfies the Katz-Tau convex Wolf axioms if whenever you take a convex set V, you could ask how many sets from my collection W are contained inside V, and you add up all their volumes, and that's at most perhaps up to a constant, the volume of V. So this is a type of anti-clustering condition. It's saying the sets in Blackboard bold W are not allowed to hide, they're not allowed to cluster too much inside of a larger convex set. And Hong in one of her talks also mentioned something called the Frostman convex Wolf axioms, and that's closely related, but on the right-hand side you have a normalization factor, which is the sum of the volumes of all the sets in W. And these both play an important role in our proof. So this is a bit of a mouthful. I mean, convex has to do with the class of objects you're considering as convex, and Wolf comes in because Tom Wolf played an important role in the Kakeya problem, and he had a similar-ish condition. And then there's different kinds of non-concentration conditions that arise when you're trying to discretize questions in fractal geometry or geometric measure theory. And one of these concentration conditions is often called a Katz-Tau non-concentration condition. So that's where that comes in. So with that definition, I can tell you what Hong and I proved. So in 2 dimensions, Cordoba proved the discretized Kakeya set conjecture. Davies proved the original version, and perhaps implicit in his proof is the discretized version, but explicitly Cordoba proved it in the 70s. And in 3 dimensions, Hong and I recently proved this result. And what it says is, if you have a collection of delta tubes in R3, is what Hong and I proved, and R2 goes back to the 70s, that satisfy the Katz-Tau convex Wolf axioms, then you have the desired volume inequality. And in particular, if you have delta tubes pointing in delta separated directions, it's not hard to convince yourself that they satisfy these Katz-Tau convex Wolf axioms. So this result in particular applies to delta tubes pointing in delta separated directions, and this implies the Kakeya set conjecture in R3. As I've written it, it implies that every Bezukovich set in R3 has Minkowski dimension 3, and we actually prove something a little bit more technical. So for those that know what the Kakeya maximal function conjecture is, we don't prove that, but we prove a weaker statement in that direction, which in particular implies that every Bezukovich set in R3 has Hausdorff dimension 3. So that follows from our work. But I'll just talk about this version involving tubes and the entirety of tubes in their union. Okay, so the moral of this theorem that I've written right here is up to logarithmic factors of Bezukovich compression, unions of tubes, or more generally unions of convex sets in R2 and R3 are disjoint unless they cluster into bigger convex sets. So that's the only obstruction to disjointness, at least up to logarithmic factors. And as Ruchang previewed in his talk a few minutes ago, that statement makes sense. So this theorem that I've written, which is true in n equals 2 and n equals 3, the statement makes sense in R4, but it is a false statement. And the counterexample is exactly the counterexample that Ruchang described. You have this variety Z, which is a quadratic hypersurface in R4. You take its delta thickening, you intersect with a ball, say the ball of radius 2. And the variety Z contains a 3-parameter family of lines. And so its delta thickening contains, intersecting with the unit ball, contains roughly delta to the minus 3 delta tubes. And if you take all of them, okay, they don't satisfy the Katz-Tau convex Wolf axioms, but you can take a fairly large subset, cardinality delta to the minus 5 halves, and it will satisfy the Katz-Tau convex Wolf axioms. But the sum of the volumes is substantially bigger than the volume of the union. So the statement is false. There's there's a counterexample to another statement, which is you could ask this theorem, you could state the theorem over C3 instead of over R3. If you adjust things appropriately, the statement makes sense, and again the statement is false. The counterexample is something that Hong might have mentioned. It's called the Heisenberg group example. I'll talk about that a little bit later. But that's if you think of C3 as R6, this is some quadratic hypersurface in R6. And so again, these quadratic hypersurfaces that contain a lot of lines or a lot of hyperplanes play an important role. So I could re-ask my question 1, but a more specific form, question 2, in R4 or more generally in Rn. So what are the hypotheses needed to ensure that unions of tubes are almost disjoint? So what are the obstructions? And so this is a specific obstruction in R4, and you might imagine that this and convex sets are more or less the only obstructions. There is some evidence in favor of that possibility. In higher dimensions, you can try to understand what's going on. There's an increasingly large zoo of algebraic varieties that contain a lot of lines. If you thicken them, you get semi-algebraic sets, and maybe that's the right class of object to think about. Or maybe you really have to wander into that zoo and start to wrestle with each one of these objects and try and understand them better. So there's interesting questions there. Some of it in that sort of classical Italian algebraic geometry school. Exactly what are the correct class of obstructions to think about if you care about Kakeya in higher dimensions. We don't understand that very well. What I want to talk about now is the solution to, or bits of the solution to Kakeya in R3. And the picture really starts back in 1995, at least gets seriously started in 1995. So Tom Wolf proved that every Bezukovich set in 3 dimensions has Hausdorff dimension at least 5 halves. Then around 2000, 2001, Katzwaba and Tau made a small improvement to that. They proved that every Bezukovich set in R3 has upper Minkowski dimension, at least 5 halves, plus some small epsilon naught, maybe 10 to the minus 10. Chris mentioned this as well in Ladaccio. And getting from 5 halves to 5 halves plus a little bit was actually quite difficult because, as I mentioned before, there's this object which looks a little bit like a Bezukovich set. It's in C3 instead of R3, but okay. which sort of genuinely has dimension 5 halves. So their proof had to distinguish this near miss to the Kakeya set conjecture from a genuine Kakeya set. And what Katswaba and Tao did in their proof is they started by saying, okay, imagine there was a genuine Bezikovich set of dimension exactly 5 halves. It would have to have these 3 structural properties that they call planiness, graininess, and stickiness. And then with a huge amount of work, they showed that such a counterexample in dimension 5 halves would have to resemble this Heisenberg group example, and after yet more work, they showed that that was impossible. They extracted a small quantitative gain. So what planiness says is you have some, so you imagine you have some counterexample to the discretized Kakeya set conjecture. You have a union of delta tubes. Look at a typical point, look at the delta tubes passing through that point. To be plane, he says most of those tubes are roughly coplanar up to a certain resolution. There's a few different interpretations of graininess, but one interpretation is as you move that base point around, the plane is not changing too quickly. And so the Bezikovich set can be written as a union of rectangular prisms of certain dimensions. Stickiness is perhaps the most interesting, and it's illustrated by this picture here. You have these delta tubes pointing in maybe in delta separated directions. And if you consider larger scales rho, so here red represents rho tubes. Rho is some scale bigger than delta, less than 1. And you could ask how many rho tubes are needed to cover my collection of delta tubes. And by cover, I mean I want to find a set of rho tubes so that every delta tube is contained in at least one of the rho tubes. And you could imagine certain configurations of delta tubes can be covered quite efficiently, and others cannot be covered efficiently. By efficiently, I mean it doesn't take too many rho tubes to do this cover. And so let's just think a tiny bit about numerology. So we're in R3. These delta tubes point in delta separated directions. To make our life easy, let's imagine there's delta to the minus 2 of them, which is roughly the maximum number. And you could ask, what's the smallest possible number of rho tubes needed to cover these delta tubes? And you can pretty quickly convince yourself you're always going to need at least rho to the minus 2 of them. And why is that? Well, the directions of delta tubes inside of a rho tube, they're constrained. There can be at most delta over rho to the minus 2 of these tubes in a rho tube. That also follows from the Kastel convex Wolf axioms. So you need at least rho to the minus 2 of them. And if that lower bound is more or less obtained at every scale rho, you say you're sticky. And if it's not obtained, you say you're not sticky. So any given configuration of tubes might be sticky or not sticky. Being sticky is rather special, but as we'll see, this special property plays an important role in the proof. So hopefully the definition makes sense, at least at the level of this picture. Okay, so maybe I'll back up. The Katz-Tau program for proving Kakeya in R3, step 1 was say, okay, imagine you have a hypothetical counterexample to the discretized Kakeya set conjecture in R3. That counterexample has to have these properties of planiness, graininess, and stickiness. And this was this idea that Katz and Tau thought about for a while following the Katz-Tau proof, and so in the early 2000s. And around 2014, Terry Tao gave a very influential talk at ICM where he outlined this Katz-Tau program that he and Nets had been thinking about. I guess at that point they'd more or less stopped thinking about it. They were willing to share it with the world. And they said, here is this idea we had for how to prove Kakeya in R3. And so step 1 is show that every counterexample has these 3 properties. And in the intervening years, from 2000 to roughly when Terry gave his talk, it had been shown that any hypothetical counterexample to the Kakeya set conjecture does have to be plany. That's a result of Banach-Harborian Tau on multilinear Kakeya. It's the contrapositive of their theorem. And in R3, that any counterexample to Kakeya, if it existed, would have to be gradient. And that was this very nice structure theorem of Larry Goof, which says if you have a union of tubes and their volume is smaller than them being disjoint, you have to have this gradient structure. It wasn't clear that a counterexample to Kakeya in R3 would have to be sticky, and that was a rather big problem for this Katz-Tau program because the starting point requires these 3 properties. So the first thing that Hong and I did is we considered how can we follow this Katz-Tau program while sidestepping this rather serious problem that we don't know how to establish that a counterexample to Kakeya has to be sticky. And one way to sidestep the problem is just to change the problem and restrict your attention to arrangements of tubes that are just sticky by fiat. And that's a well-defined collection of tubes. And we proved something called the sticky Kakeya theorem. So this 2026 seems more recent, but the chronology is coherent. We proved this result in 2022. And it's that the discretized Kakeya theorem in R3 is true if you restrict attention just to sticky collections of tubes. And I want to tell you a little bit about some of the ideas behind this proof. And so what we'd like to do is, you can think of it if you want as a proof by contradiction. So this inequality here, the left-hand side is the volume of the union of the tubes, the right-hand side is the sum of the volumes of the tubes, and we have this double squiggle which hides subpolynomial factors. And we define beta to be the smallest non-negative number, so that an inequality like this always holds with a loss of delta to the beta whenever you have a sticky collection of tubes. And our goal is to show that beta equals 0. That is exactly the sticky Kakeya theorem. But you could imagine that this is not true and there's some strictly positive beta for which this holds, and try to arrive at a contradiction. And the statement I have here is an inequality about volume, but if you want, you can think of it as an inequality about multiplicity. So here, mu of tau is the typical multiplicity. So I have this arrangement of delta tubes in R3. I look at a typical point in that union, and I ask how many tubes pass through that typical point. I'm going to define that to be mu of tau. And after pigeonholing and imagining every point behaves the same as every other point, this is like the sum of the volumes of the tubes divided by the volume of the union. So it's the same delta to the beta, except one is the reciprocal of the other. So our goal is to show that beta is 0. We'd like to prove that. So the idea is, so suppose that beta is bigger than 0, i.e. there is a sticky collection of delta tubes whose union has volume much, much smaller than the sum of the volumes by some delta to a positive power beta. And I want my collection of tubes T, I want to take a worst case counterexample. So I want to imagine that inequality is extremized, or at least close to extremized. And I want to analyze what happens. So on the left here, I have this sticky collection of tubes, and in red I've shown some row tubes to give a sense of what's going on. And a useful operation is I can take one of these row tubes and I can apply an anisotropic rescaling, which sends it roughly to the unit mole. And so what used to be delta tubes inside of my row tube become now tubes of thickness delta over rho contained roughly inside of the unit mole. And it's not too hard to show that if my original collection of delta tubes was sticky, then these row tubes are also sticky. They have the same multi-scale efficient covering property. And it's also true that if my delta tubes are sticky and I restrict attention to the delta tubes inside of a row tube and I rescale, I get these new delta over rho tubes, these blue ones, they will also be sticky. And that's a computation which is also not too hard to show. And now I can do the following. I can say, what is the intersection multiplicity of these delta tubes? Right? Take a typical point in my union of delta tubes. How many delta tubes pass through it? Well, almost by definition, that's delta to the minus beta, because I started with this worst case configuration. But I want to bound this from above in the following way. I want to ask how many row tubes pass through a given point. And for each one of those row tubes, how many delta tubes inside of that row tube pass through that point. And that product is going to be an upper bound for this quantity. And those are both objects I can control because those row tubes are sticky. So the intersection multiplicity is at most rho to the minus beta, because beta is defined to be an upper bound that always holds whenever you're sticky. And how many delta tubes pass through a given row tube, that's the same as the intersection multiplicity of these blue guys here. That's at most delta over rho to the minus beta, because again, I have a sticky collection. And that's delta to the beta. So everything here is more or less an equality. And so this was really a starting point of this cat's tau program. Observing you have this equality here, and then trying to understand what this tells you. And it turns out it tells you a lot of structural properties about this family of tubes. And what it means is that my original, so if you have a collection of tubes, which is a worst case counterexample, then whenever you thicken it at a scale rho, you get another worst case counterexample. And whenever you thicken and then zoom in on the delta tubes inside of those rho tubes, you get another worst case counterexample. So the whole arrangement is sort of coarsely self-similar. And what do I mean by that? So the middle thirds Cantor set is literally self-similar. But if you were to apply, say, a bounded Lipschitz map to the middle thirds Cantor set, you've wrecked all the arithmetic structure, but you've kept a lot of the statistical structure. So this is what I mean by coarsely self-similar. And another example of, you take the middle thirds Cantor set, you apply some bounded by Lipschitz map to it, you get something called a Alfors to be regular set. And I'll define that for you in the discretized setting. Hong mentioned it as well. So a set is Alfors to be regular. Let's say it's a union of delta balls, so everything's discretized. What this means is whenever you take a point in your set E, and you take some radius between delta and 1, and you ask how much of your set is contained in the ball centered at a point of your set, critically, with radius r, it scales like r to the alpha times E, where r to the alpha, where the exponent alpha is telling you how much of your space is filled out. So an example is the middle thirds Cantor set, but you can also take the middle thirds Cantor set, apply a by Lipschitz map, right? You preserve this property. And A very important theorem for Bourgain is called the discretized sum product theorem. So there's this conjecture of Erdős and Volkmann, and they asked, are there any subrings of the real numbers of Hausdorff dimensions strictly between 0 and 1? And the answer is yes, but they're really pathological, so you back up. Are there any Borel subrings of the real numbers, so dimensions strictly between 0 and 1? And there the answer is no. And this was proved by Edgar and Miller. And shortly thereafter, Bourgain proved a more quantitative version of this statement. And what I've written here is a special case. He proved it from more general sets, but I'll just give you this special case. So let's say I have a union of delta intervals, which is a subset of the interval from 1 to 2. I want to stay away from 0 because multiplication behaves badly around 0. You take this union of delta intervals and you could look, let's imagine it's alphas regular with exponent alpha. And it's a union of roughly delta to the minus alpha delta intervals. So it has cardinality, or it has volume delta to the 1 minus alpha. You could look at the sum set, which is what you get by adding every pair of points together. You could look at the product set. Both of those are themselves going to be collections of intervals. And at least one of these has to grow substantially. And by substantially, I mean delta, like delta to a negative power. So for those that are familiar with the Erdős-Demeretti sum product theorem, that is the analog of this where you're working over the reals and cardinality is used instead of measure. And Bourgain proved this discretized version. So it's a bit of a walk. This theorem plays an important role, and in particular, this theorem distinguishes the real numbers from the complex numbers. Because over C, a very similar statement makes sense, but it's false. You take all of the real numbers as a half-dimensional subring sitting inside of C, and the statement written here makes sense, but it is a false statement. So this theorem distinguishes R from C, and that's important because I already told you that earlier there's this near miss to the Kakeya set conjecture where instead of working in R3, you work in C3, and you take this 5-dimensional quadratic hypersurface in R6, which I identify with C3, and this has many of the properties in common with a Bezukovich set. But this Heisenberg group example makes really critical use of the fact that the complex numbers have this half-dimensional subring sitting inside. I didn't write down the definition of the Heisenberg group example, but it involves complex conjugation. It uses this involution. And so this theorem of Bourgain plays a very important role in distinguishing R from C. And backing up, a Bezukovich set in R3 is a union of lines. And if you write down the definition of a line, you might believe me when I say lines mix addition and multiplication together. And so it's not entirely shocking that if you have an arrangement of lines whose volume is illegally small, or a union of double thickened lines whose volume is illegally small, then from this eventually you can extract some sort of counterexample to Bourgain's discretized sum product theorem. So there's a long walk there in which I'm hiding most of the proof, but it maybe gives you a sense of what's going on in this sticky setting. For those of you that have seen Alekish's proof of getting a sum product bound using Demeretti-Trotter, it's perhaps not entirely shocking that lines mix addition and multiplication, and there's a connection there. I'll say as well, in the original Katz-Tau program, the original Katz-Tau program for proving Kakeya in R3, they described this reduction to Bourgain's discretized sum product theorem. And Hong and I took a slightly different path, where we instead reduced to a question in discretized projection theory in the plane, and somehow that was a more efficient thing to do. But if you walk that whole thing back, at the end of the day, you have to distinguish R from C in some way, and Bourgain's theorem is looking in the background. Bourgain's had a very profound influence on this area in many directions, and this is just one of them. So that's all I want to say about the sticky Kakeya theorem. And now a question we can ask is, how do we go from proving the sticky Kakeya theorem to the general Kakeya theorem? And I'm going to talk very briefly about Hong and my proof. And this was later simplified by some ideas by Debbie Booth. And so the three of us have written a more streamlined version of that proof. And what I'm going to talk about here draws from that more streamlined version. There's also a reinterpretation of many of the ideas by Alex Cohen. This has affected our thinking since then. So all of these ideas have played a role in what I'm going to say here and also our ideas going forward. So we could also try to prove the result by contradiction. So we could imagine I have some positive number sigma, which is the smallest constant, such that And I have something very similar, right? So this is the left-hand side is the volume of the union of tubes, and the right-hand side is the sum of the volumes. And before I had something like delta to the minus beta, and here I have the number of tubes, which is certainly controlled by delta to the minus 2. It might be substantially smaller to the minus sigma. And our goal is to prove that sigma equals 0. If you could prove this statement is true for sigma equals 0, we have proved precisely the discretized Kakeya set conjecture. But this ends up being a useful formulation, a useful way to think about the problem. And again, any volume bound can instead be thought of as a multiplicity bound. And so I've written this on the right-hand side, the equivalent multiplicity bound. So our goal is to show that sigma equals 0. And I have to apologize. For some reason, sigma became beta on this slide. But I replaced all the betas with sigmas. And I'm more or less, so it's a fairly long proof, and I'm going to compress it into a single slide and try to explain to you what this slide is saying. And so you give me an arrangement of tubes, and we could imagine, if you want, that this is a worst possible arrangement of tubes. So maybe it extremizes this inequality here. And if you want, just to make life a bit easier, we could imagine there's roughly delta to the minus 2 tubes in this arrangement. That's a special case, which is a bit easier to think about. And we want to understand what's going on. So I have this arrangement of delta tubes. They satisfy the Katz-Tau convex Wolff axioms. And if they were sticky, I could immediately apply the sticky Kakeya theorem and conclude that the multiplicity is what I want, the volume is what I want, and I'm done. So presumably the interesting case is when this arrangement of tubes is not sticky. And what does that mean? It means there's at least one scale rho which witnesses this failure of stickiness. And in our actual proof, it's helpful if there's many scales rho which witness this failure of stickiness. But for the moment, let's just imagine I have this scale rho, which are these red tubes. And what does it mean to not be sticky? It means there's far more than rho to the minus 2 rho tubes required to cover these delta tubes. And what that means is the number of delta tubes inside of a typical rho tube is substantially smaller than delta over rho to the minus 2, right? That would be the maximal possible packing. That's what occurs when you're sticky. If you fail to be sticky, then you're substantially away from that. And that seems a little bit promising, because as we've seen, an inequality of this form, the amount we're losing depends on the number of tubes to the power of minus sigma. And so it seems at least possible that if you zoom in on the delta tubes inside of a rho tube, which are witnessing this failure of stickiness, we might be able to exploit the fact that there's fewer delta tubes inside of a rho tube than you might expect. And that's going to be an important aspect of the proof. What we did in the proof of sticky Kakeya, just to back up briefly, is we bounded the multiplicity of the tubes by the product of the multiplicity of the rho tubes times the multiplicity of the delta tubes inside of a rho tube. And that didn't quite finish the proof for us, but we had more or less equality, and this gave us a lot of structural information. And you could try to do a similar thing if you fail to be sticky and try to understand what happens. So if you're far from being sticky, this blue term here is a little bit better, because there's fewer delta tubes than you might expect inside of a rho tube, so you're getting a bit of a gain there. But unfortunately, that gain is very much dwarfed by the fact that there are far too many rho tubes. It's not even clear that these rho tubes satisfy any of the hypotheses needed to apply any sort of induction. And even if it did satisfy those hypotheses, because there's so many rho tubes, you would get a catastrophically bad bound. And so not only do you fail to get equality on the right and left and get some sort of structure, you're getting a much worse result out than you put in. So this is not a good idea. And so a question which applies to many problems where you're trying to use induction on scale is, if you fail to be sticky, which means at larger scales you have far more objects than at finer scales, how can you use induction or induction on scale to prove estimates? Because just controlling things by what's happening at coarse scale times what's happening for fine objects inside of a coarse object, that is not an efficient equality. So I want to jump back to this last slide and go to this arrangement of delta tubes, which fails to be sticky. So there's far more rho tubes than you might expect required to cover these delta tubes. And I want to understand, how can I say something more precise or more intelligent than just the number of delta tubes interacting with each other coming from different rho tubes is controlled above by just the number of rho tubes, right? It's always true how many delta tubes pass through a point? Well, it's the number of row tubes passing through that point times the number of delta tubes inside of each row tube passing through a point. That is not very efficient. The number of delta tubes passing through a point inside of a given row tube, this is what I'm going to call mu fine. And I have this new quantity mu coarse, which is going to control how many different row tubes can contribute to a given point. And I need a more efficient estimate for that than just how many row tubes contribute to a point. And this is the key new idea. And so the way we estimate that depends a little bit on how these tubes are arranged. But I want to focus on one special case. So what I've drawn here is I've drawn a blue ball. And I want to think of this blue ball. So everything takes place inside of roughly the unit ball. And this blue ball is substantially smaller than the unit ball. Maybe it has radius something like delta to the epsilon, where epsilon's a scale that I get to choose. I'm going to focus on this blue ball. And for each one of these row tubes, I'm going to look at the delta tubes inside of that row tube, but I'm going to restrict my attention to this blue ball. And I'm going to ask myself, how do these delta tubes arrange themselves? And there's many possible ways they can arrange themselves. But one particularly interesting way is they arrange themselves a bit like wooden matches inside of a matchbox. So wooden matches inside of a matchbox, if you leave them straight, are all perfectly aligned with each other. But if you empty a few matches out and then shake up the matchbox, they're sort of all jumbled in various ways, but they're still constrained inside of that matchbox. And that puts substantial constraints on how those tubes can be arranged inside of that matchbox. And so what I've drawn here, these purple objects are the matchboxes. And the delta tubes, so each one of these matchboxes is coming from one of these red row tubes. The same row tube might contribute several matchboxes, but I've only drawn one each. And the delta tubes inside of these red row tubes are the matches, the jumbled up matches inside of those matchboxes. And that seems like a rather special situation. But one of the ingredients involved in my proof is a structure theorem, which more or less says, if you give me an arrangement of matches, then either these matches satisfy so those are convex ones, either they satisfy the Kakeya Wolf axiom, in which case we're rather happy, or they are arranged, they're jumbled up inside of matchboxes. You can find these matchboxes, and the matchboxes satisfy the Kakeya Wolf axioms, and the matches inside the matchboxes might be rather dense, but they satisfy something called the Frostman convex Wolf axioms. So that's what I mentioned before. So you want to imagine I have these purple matchboxes, which are coming from these red tubes, and inside they're fairly densely packed with the matches, which are the original delta tubes from my configuration. Right? Delta tubes restricted to this blue ball. Okay, so this blue ball is the same as this blue ball. The delta tubes have now arranged themselves into these matchboxes. And I want to now understand the geometry of these purple matchboxes. And so I've written this as G, sometimes G refers to grains. And so here's what's going on. Mu fine here is the number of delta tubes from a row tube that pass through a common point. And mu coarse is the number of matchboxes, the number of these purple objects that pass through a given point. And I claim that that gives me a bound for the original intersection multiplicity of the delta tubes. And here's why. So take a point in R3. I want to understand how many delta tubes pass through it. Those delta tubes came from different row tubes. How many delta tubes come from the same row tube contributing to a given point? That is mu fine by definition. How many different row tubes contribute to that point? Well, I could bound that by the intersection multiplicity of the row tubes, but a better idea would be to say, okay, every delta tube passing through a given point is in one of these matchboxes, and that matchbox came from a row tube. So if you look at just the matches inside of a matchbox, right, the delta tubes inside of one of these purple guys here, how many delta tubes are allowed to pass through a given point? That is mu fine. And how many matchboxes pass through a given point? Well, I'm just going to call that mu coarse. That's my definition of mu coarse. So mu fine I have a pretty good estimate on because I'm far from being sticky. So fewer delta tubes pass through a row tube than you might expect, and that seems promising. But I need to control I need to control mu coarse. I need to control how many of these matchboxes pass through a given point. And there's different ways these matchboxes could interact with each other. But one possibility is they could be tangential, and that's maybe the most interesting situation. Right? So a matchbox is much thinner then it is wide. So there's a two-plane associated with that matchbox. And by tangential, what I mean is whenever two matchboxes intersect each other, their corresponding two planes agree, at least up to the uncertainty that they're defined. And when that happens, then there's a very natural rescaling, which is all the matchboxes more or less agree in their two-plane until we anisotropically dilate in the direction of that two-plane. And then we might as well dilate that blue ball to be the uniball for good measure. And if you do this computation carefully, you actually end up with an arrangement of row tubes, which is very nice because the starting point for this whole thing was an inequality involving row tubes. And this factoring theorem I mentioned, what it tells you is these matchboxes actually obey the Kakeya Wolf axioms, and that is invariant under all these rescalings. That's one of the virtues of this definition compared to double separated directions, is it is invariant under these rescalings. And so now I have a new Kakeya problem. I have my Kakeya problem about the delta tubes inside of a row tube, and I have my Kakeya problem about these row tubes, which weren't the red row tubes, they're the rescaled matchboxes. And this is where the gain comes from. So I'm a little bit over, so I'll just very quickly walk you through this computation. So I have the original multiplicity of my family of tubes. This is what I'd like to control. And it's controlled by mu phi, which is the intersection multiplicity of the delta tubes inside of a row tube, or equivalently, how many matches inside of a given matchbox all pass through the same point. And then I have mu course, which is how many matchboxes pass through a given point, which is the same as a new Kakeya problem involving these rescaled row tubes. And I don't know exactly how many rescaled row tubes there are, but I know that they obey these Kakeya-Wolf axioms, and that gives me control on the cardinality of this set. And I just plug in that rather coarse estimate, that crude estimate, which is this guy right here, delta to the -2, also the beta. And here's where I'm making crucial use of the fact that I am far from sticky. So the number of delta tubes inside of a row tube, it's less than you would expect, so I get this little gain, which is rho to the c, and that is a gain in the correct direction. So on the left-hand side, I had the multiplicity of my tubes, which I was assuming was the number of tubes to the beta, and now I've got a small improvement. I have rho, which is the scale at which you witness this failure of stickiness, which is a small constant, times the number of tubes, raised to delta to the beta. So either I have a contradiction, this wasn't the worst case example, or if you want, if I assume that beta was the best exponent for which I knew this result was true, I've now improved my beta a little bit. Two equivalent ways of thinking about it. Okay, I'll finish there. Thank you.